Hello, folks, and welcome to today's webinar. We're going to be kicking things off in just a moment. I still see a bunch of people trickling in, so we'll probably give them another 30 seconds or so and then start going through some of the logistics and introductions. So thanks everyone for dialing in. Maybe while the room is filling up in the chat, if people would love to say hello, say where you're dialing in from. We love from Italy, wonderful. Bangalore, welcome. We love pulling an audience from, all over. So we're happy to see you all. Cancun, Seattle, Belgium, welcome. Wonderful. Love to see it all. Excellent. So I'm going to go ahead and talk through a few logistics for this webinar. If you've been to a Predibase webinar in the past, this will be familiar, but a few things that are worth noting. First off, all lines are muted. We will have a Q&A through the chat at the end, but the lines are muted just to keep things flowing smoothly. Also, this is being recorded, and the webinar will be put on our YouTube page afterwards, most likely later today, so that you can rewatch it in your leisure. You'll see throughout the course of the webinar, we're going to kick these off in just a couple minutes, a series of polls that are going to show up on the right side of your screen, just to kind of get a better sense of who's in the audience and to make sure that we're building content that's really relevant for the folks who are coming to our webinars. So asking a little bit about your AI and ML initiatives. The results of them are shared anonymously, so you'll be able to kind of see who, what the answers are to those questions, but you won't see, of course, who's answering which question. And also the chat, you'll notice, is a public chat. So feel free, we love having public chats. We get people engaging with each other, making connections. We do have some folks from Predibase who are in the chat today. So if you have questions, feel free to ask them in the chat as we're going. And some of our teammates will try to answer them, as quickly in real time as possible. Otherwise, we will also have some dedicated time at the end for a more formal Q&A. Let's see if y'all could flip to the next slide real quick. Lastly, thank you. Also, you'll see, Predibase, we have a free trial that it's a month-long free trial that comes with $25 of free credit for you to fine-tune and serve models. So you can see the link right there, or you can just go to predibase.com and hit the Get Started button to start your trial if you're interested. Everything that we walk through today, you'll be able to work on yourself if you want. So now go to the next slide for some quick introductions, and then we'll get the show on the road. So we're joined by Justin and Timothy. They're on our engineering team. Justin is one of our founding staff engineers at Predibase, and Timothy is one of our ML engineers. And the two of these guys are really foundational to the work that we're going to be talking about today, LoRA Land. Hopefully, many of you in the audience saw LoRA Land when we announced it a week ago last Tuesday, and maybe you've been able to even play with it on your own. But without further ado, we're going to dive into today's webinar, and Justin's going to kick things off, giving a little bit more context around LoRA Land and telling you a bit more about what we built. So, Justin, over to you.
Thanks, Will. Great to be here again and to be presenting LoRA Land for you. So LoRA Land is this big launch that we did, and it's the result of hard work across all the teams here at Predibase. And Tim and I, we prepared you sort of these nice slides to talk about all the details of the playground that we built. The playground is 25 Mistral-7 billion adapters that we fine-tuned across many different tasks. And their performance in terms of quality, by and large, rival that of GPT-4. And so by rival, we mean like equal or better. And so today we'll talk about how we got that. So in this LoRA Land work, we kind of aim to demonstrate 4 things. 1, smaller fine-tuned models can consistently outperform larger generalist models, including GPT-4. This, for those of you who have been in the world of model distillation and machine learning, this shouldn't be news to you, but I think the first demonstration of this was back in 2014, but it's worth reiterating. Fine-tuning is really powerful. Second, we wanted to demonstrate the broad flexibility of specializing many models using the same base model, using a technique called parameter-efficient fine-tuning, called QLoRA. And then to put our kind of money where our mouth is, we wanted to actually launch like a real fast performant production application that serves many specialized models with real world traffic. And then lastly, we wanted to show that we actually can serve all 25 of these LLMs on a single GPU using LoRAX. This is a technology that takes advantage of these PEFT mechanics to efficiently load multiple sets of adapter weights. And we'll talk more about that later. Cool. So first, to understand the need for an efficient way to fine-tune large language models, let's first look at where we use fine-tuning in this machine LLM training process. The first part of creating a large language model is pre-training. So pre-training is when we take a very large amount of text, like 1 trillion words, and the model just kind of churns through all this text, learning to predict the next word. And then pretty much everything after that is fine-tuning. So for example, once we have a good pre-trained base model that kind of understands, some grammar and understands how words correlate with each other, then we start fine-tuning with, for example, instruction tuning to get the language model to be effective at following instructions. And this is how we get super fun chat models like ChatGPT. From there, we can take these models even further and fine-tune them more to do very specific tasks super well. And this fine-tuning process is really powerful. And because we can specialize to many different kinds of tasks, the possibilities for fine-tuning are limitless. But in the world of fine-tuning LLMs, you have this dichotomy between traditional fine-tuning and something called parameter-efficient fine-tuning. In normal fine-tuning for large language models, you have your data set, and you're aiming to update all 7 billion or how many ever parameters you have in every single training step. And this is very expensive from both a memory perspective as well as a runtime perspective, because all of those parameters you have to track updates for, and then you also have to apply those updates. But there's this alternative that essentially says, instead of adjusting all of the weights of the model, I'm just going to adjust a very small percentage of the weights that I've introduced as new weights and fine-tune those. And so the result is that we can keep the base model the same, and then the new set of weights we call an adapter is very small, usually on the order of 1% or so of the total model parameters. One of the most popular adapters out there is called Low Rank Adaptation, or LoRA. And in this technique, we basically introduce 2 new tensors alongside layers in the original model. You keep the pre-trained weights completely frozen, and during backpropagation, you only update the new tensors. Each of these tensors is very small. And when you multiply them out using a concept from linear algebra called matrix decomposition, that's how they end up with the same shape as the original pre-trained weights. Here is an example of how we might decompose this weight matrix with rank 1. And the higher rank you choose to decompose by, the more information you have when reconstructing the full weight matrix. And then once we have these weights in the same shape as the original pre-trained weights, we simply add them together, and then that's how you get your final fine-tuned weights. The parameter savings from LoRA matrix decomposition have been really significant, they become really significant when your weight matrix is large. And this high efficiency is part of the reason why LoRA is so popular as a parameter-efficient fine-tuning technique. But then the other reason why LoRA fine-tuning is popular is that it's been shown that it's just as good as full fine-tuning. So this is a table from the original paper where we see that across all these data sets, LoRA is extremely competitive, to say the least, to full fine-tuning. And all the while, the number of trainable parameters is less than 1% of the total model size. The last trick to make adapter-based fine-tuning even more efficient is to use 4-bit quantization. There's a lot of interesting details in this paper that we're not going to go over today, but a few things to mention. Gradients are still computed just for the LoRA parameters, and essentially you're just storing all your model parameters in 4 bits. You dequantize your parameters to 16 bits to perform computations in the forward and backward passes, but really the weights are decompressed only when they're needed, and therefore memory usage stays super low during training and inference. So that was a deep dive into, or a quick overview in terms of like the anatomy of an adapter, which in summary is a small set of trained model weights produced during fine-tuning that's used to specialize a pre-trained base model. So now I'm going to hand it off to Tim to talk about some of the methodology behind how we trained adapters in LoRA Land.
Perfect. Thank you, Justin. So next slide, please. I'm going to start by going over a little bit of our dataset selection. So as you can see on the screen here, we had about 27 datasets that we fine-tuned on. We selected our datasets from ones that are either commonly used as LLM benchmarking or ones that serve as proxies for industry tasks. These are all commonly available either on Kaggle or Hugging Face, so on and so forth. So here you can see some tasks such as Jigsaw, which is used for toxicity prediction. We have SQL generation. We also have for the LLM benchmarks a lot of the glue data sets in QNLI and COLA that are often used just to ensure that our adapters are able to learn basic tasks such as grammar detection. If you take a look at some of these next columns, if you hit next, Justin, the mean number of tokens varies pretty drastically between some of these data sets. So we have tasks that range from really short text to pretty long documents. And if you take a look at the next column over, many of these data sets have fairly long tail distributions. So we needed to omit some of these small numbers examples where they are exceedingly long. So to maintain that balance between longer sequences and having computational efficiency, we train our models with P95 percentile of the maximum text length. Next slide, please. This is our config. For any of you who have used Predibase or Ludwig, our fine-tuning centralizes around this configuration file. This YAML formatted configuration specifies exactly how our fine-tuning should run. So a few things that I wanted to point your attention to. Number one is our prompt template. This is how we format our inputs. So you'll see, I'll go a little bit deeper into this in our next slide, but for now you can see just kind of an example of how we format our inputs. Next, you can take a look at our adapter section here and notice that we have set the type of our adapter to LoRA, as mentioned by Justin earlier. And lastly, if you take a look at our quantization there, our quantization is mainly meant to help further make our fine-tuning efficient by setting everything to 4-bit quantization in this example. And these are mostly our defaults. So you really don't have to do much to the fine-tuning configuration that we provide you. And I'll show you later on just how easy it is to fine-tune with Predibase. Next slide, please. So how did we choose our prompts? We primarily wanted to ensure that we were providing fair evaluation between GPT-4, our other models, and as well as our fine-tuned adapters. So we wanted to make sure that we provided clear, task-specific instructions that avoided simply providing just the input. For example, while a fine-tuned adapter may respond well to a single sentence and provide exactly what we wanted just because of the way it's been fine-tuned, something like GPT-4 might not know exactly what to do if we just prompted it with a sentence. So we explain exactly what the task is, and we specify what our output formats are. So here on the left, you can see that we provide the task and then the inputs, and then we specifically prompt the model to provide its outputs. On the right is an example of us using single-shot prompting in the cases of, for instance, named entity recognition, where the output is going to be more specific than what than normally it would be. So here we provide an example in the prompt to show what we want this model to output. Next slide, please. Now you might be wondering, how exactly did we determine whether or not our adapters were actually stronger than GPT-4? We stuck with the two primary metrics of accuracy for our classification tasks and rouge for our generation tasks. These are two very common metrics across many LLM benchmarks. But there were some data sets where we couldn't use just these two. In the case of our coding data sets, we stuck with human eval. This is a set of human-provided coding problems that our models would respond to. And then these would be run through a test suite to make sure that the outputs were all correct and that the code actually ran. Then we determined the accuracy of these based off just the percentage of questions that our model got correct. GSM-8K, on the other hand, was a math-based data set that we trained on. Because of the format of these outputs, we had to apply some regular expression extraction just to make sure that we actually extracted the correct answer and not any of the surrounding text around it, and then use that for accuracy. In the cases where we needed to use post-processing, sometimes our adapters would return something like an index rather than an actual class, whereas GPT-4 would provide the actual class. In this case, we just wanted to ensure that when we were calculating accuracy, we were doing so consistently. And then here on the right, you can also take a look at exactly how we got our metrics. So this was us using an evaluation harness that we created that queried GPT-4, queried our backend, returned all the responses very efficiently, and then calculated the accuracy or the rouge score based off of it. Next slide, please. Here is, I'll just show a very quick example of how we would fine tune, just to show you how easy it is with Predibase. So here you see our main menu on the Predibase website. And if you were to click on the data tab, you can upload your data here. As you can see, we have a lot of different formats that you can choose from, so you can pick whichever one you'd like. You will create a new model repository, give it a name, and then when you go next, you'll be led to this page. You might notice that we don't provide just a configuration editor. While you're able to do so if you're an advanced user, really all you need to do is provide a prompt template, an output feature, and the model that you're going to be fine-tuning with, and you can get a model. And all we need to do now is just wait for our results. Like I said, most of our models here in LoRA Land were trained using just the defaults, so there's really not much finagling that you have to do with the config to get good results. And if you're one of those engineers who likes to launch training jobs from the comfort of, say, a Python shell or a Jupyter notebook, Predibase gives you a great SDK just to do that. And now I'll be discussing a little bit more about our results. So here on the screen, we have the average quality of GPT-4 on the left and the average quality of our Mistral 7 billion adapters on the right over all of our tasks. As you can see, it's a pretty significant jump in performance, even with a lot of the details abstracted away in the average. But of course, we want to know a little bit more about what's going on underneath the hood. So I'll do a little bit of a deeper dive into what we've observed. Here on the screen, you see a rough categorization of the types of tasks that we fine-tuned on. We have classification, generation, math, and coding. From left to right, these are generally the tasks that we observed were to be easier to beat GPT-4 to harder to beat GPT-4 on. Regardless of the task, however, fine-tuning achieves significant lift. In general, however, the narrower the task was, the more performance improved through fine-tuning. This also tended to be the trend as to how easy it was to beat GPT-4. Adapters fine-tuned on these narrower tasks tended to more easily outperform any of their competitors, whether that be Mistral 7 billion Instruct or any of the GPT models. Next slide, please. Here are all of our model results. In the vast majority of cases, our fine-tuned adapters outperform their counterparts, as you can see from that bolded column under fine-tuned. Critically, our fine-tuned adapters vastly improved upon the base model, which is the far right column, Mistral 7 billion. And even against the instruction-tuned Mistral 7 billion Instruct, our adapters' performances were stronger on every task, with our task only being shifted a little bit on against the GPT models. Next slide, please. This is just a graph of the differences in performance between us and GPT-4, in case you wanted to see just how large a percentage difference this was. And we ended up getting a percentage difference as high as 91.5% on the upper end of it. Cool. And now I turn things back over to Justin for productionization.
Cool. Thanks, Tim. So as Tim mentioned, we've trained all of these specialized models. We've measured them on quality, and we find that most of them are better than GPT-4. And we didn't even really try and finagle with the model parameters, as Tim mentioned, just using defaults right out of the box. And so this whole exercise is already making it pretty worthwhile. But we're actually trying to build this real application in production. So what does that actually mean in terms of our costs? So with Predibase, there are two categories of costs that you incur when you choose to go with a fine-tuning specialized models solution and using them instead of kind of the out-of-the-box generalist models. And so the costs on one hand is the actual cost of fine-tuning, and the second cost is model serving. For fine-tuning, Predibase charges a price per million tokens that depends on the size of the model. And so for LoRA Land, we trained all of our models on the Mistral-7 billion model, which comes out to 36 cents per 1 million tokens. And with the default model configuration parameters, this comes out to less than $8 per adapter. And so you might be wondering, why didn't we train models on something larger? And so there are two reasons for this. One is there's actually this theory that many specialized tasks are intrinsically low rank. These pre-trained base models have already been trained on a ton of information, and they have all these parameters. And so for many tasks, they're already sort of bigger than they need to be. And two, in one of our LLM fine-tuning distillation best practices, we recommend starting with something simple and small. And it's the reason for this is that it's just valuable to see how good our specialized models can be with just a 7 billion parameter model, benchmark them there, and then before going more higher or more complex. So we talked about training costs. Now let's talk about serving costs. And this is where things get a little bit more interesting. So at the start of our presentation, I mentioned that we were able to serve all 25 7 billion parameter model LLMs for the LoRA Land website off of a single A100 GPU. In a traditional LLM deployment, you're only able to fit one LLM on a single GPU. So for 25 different LLMs, we need a cluster of 25 GPUs, right? And how in the world were we able to serve all 25 models on one GPU? To build intuition for how this is possible, let's talk about coding for a second. Hopefully, many of you in the audience are familiar with some level of software engineering, but I promise it'll still make sense even if not. So let's imagine we have this code. I promise this code is not too difficult to read, but it looks like the author is trying to define 4 different kinds of objects: a dog, a bird, a bear, and a fish. And it looks like each class defines a few methods. Do you see anything wrong with this code? So this code is actually perfectly functional, but the way it's written is horribly inefficient. And why is that? Well, it's because 80% of the code is duplicated. All 4 of these classes define the exact same 3 methods: init, eat, and sleep. And if I was reviewing this code, or if this is what you came up with during a technical interview, I would certainly have some very choice comments for you. So what you want to do instead is define a base class with all the common methods, and then define concise subclasses on top, resulting in a much more elegant and efficient representation because the duplicated code can be shared. The tons of code that you needed to separate dedicated files for can now fit neatly into probably just one file. And so this idea of sharing and polymorphism in software engineering is the exact same insight that we can apply to efficient deployments for specialized LLMs when the base model is shared. So here we see 6 separate dedicated deployments for 6 different adapters. But because they're all using the same base model, you'll notice that most of the parameters in light yellow, when they're on the GPU memory, they're actually exactly the same. So instead of having each adapter have its own copy of its base model weights on its own GPU, what if we could have all the adapters share the same base model weights on the same GPU? So this is the key idea behind LoRAX, or one of them at least, which is the ability to efficiently deploy multiple LLMs into the same deployment by sharing the same base weights. You can load all of the adapters together, And then you can maintain separate request queues for each of the adapters that can be managed intelligently with a smart scheduling system. Instead of, yeah, and so that's this key insight here. So coming back to serving costs on Predibase, Predibase gives you two options for serving your fine-tuned LLMs. One is a serverless fine-tuned endpoint, and a second is a dedicated deployment. The serverless is a pay-as-you-go option with low token-based pricing, no cold start time, or very, very small. And then, traditional dedicated deployments, you can only deploy one model per deployment. However, because of LoRAX, Predibase dedicated deployments, they enable you to serve multiple fine-tuned variants as long as all those models, adapters, are using the same base model. So let's talk about what the real production costs of LoRAX would be with all of our different options out there. What the real production costs of LoRA Land would be with all the different options out there. Tim has already confirmed for us that GPT 3.5 and GPT 4 are by and large worse in terms of quality. But let's see what it actually means in terms of production costs. If we're going to pay a ton for that extra quality, it might not be worth it. So let's make some assumptions here. We assume that each request is 90% input tokens and 10% output tokens. Let's assume that there's 100 tokens per request. And let's say that we have about 20,000 requests per day per adapter. So the more adapters that we add, we're scaling up our traffic as well. So this is what the cost kind of looks like. So the highest cost by far is the red bar, which is GPT-4. And then the second highest cost is the cost of using a dedicated deployment, one per model. So this is if you were, you had an AWS, A10G system, and you had one A10G per adapter. So we can see that the red and green bars are, far, far too high. And so let's get rid of those outrageous costs. And so, we wouldn't even consider them. And then now we have this, hopefully clearer graph where we can see that, doing a dedicated deployment, as we increase the number of adapters from 1 to 8, the cost of a dedicated deployment on Predibase is still quite high. And serverless, the red bars, give us kind of the most cost-effective option. Cool. So this seems reasonable. However, you might be thinking, hold on, that's not really a fair comparison. Because if I use GPT 3.5 or GPT-4, I don't have to incur a cost of actually fine-tuning these models. What you're presenting here is just the inference costs. And so, so we actually factor this in now. Even with the cost of fine-tuning factored in, and for us, this was $8 per adapter on average, the all-in costs are still cheaper. So the models are not only faster, but also significantly better in terms of quality, and still cheaper than GPT 3.5. The last thing I want to mention here is that there is also a nuanced trade-off between dedicated and serverless, even within Predibase's superior pricing options. So here I plotted a graph where imagine if we have, so LoRA Land was 25 adapters, so we're kind of right in this middle ground here, right before this switch. But there is a point of scale in both adapters as well as traffic where the serverless option becomes more expensive than if we had a Predibase dedicated deployment. So that's definitely something that is rather nuanced and something important to consider when you're designing your production system. However, Predibase provides you empowers you to kind of make that nuanced decision for yourself, which is awesome. And so what do we have here so far? We have this blueprint for production AI deployment. You start with this open source base model. You have the benefits of privacy and ownership. And because you're going to fine tune it, you also get better performance as well. And then for fine tuning, we're going to use parameter efficient fine tuning, which is extremely efficient, fast to train. And then because we are, make this choice up front of making sure that we all share the same base model, we can now use LoRAX, which allows us to serve many, many, many different specialized models all on the same machine and make our serving extremely cost effective. So now I'm going to hand it to Tim to talk about LoRA Land.
Yep. Thanks, Justin. If you click on that link, please. So welcome everyone to LoRA Land. If you guys haven't checked it out yet, this is what it looks like. This is our playground for you to test out all of these adapters that we trade. If you want to just take a look at these various different tasks and see our results compared to, for instance, Mistral-7b and Instruct, and you can determine for yourself whether or not you think they're stronger than GPT-4s. But here you can see that we have a whole bunch of different categories of adapters. If you click on that drop down to the left, we have different categories such as, for instance, named entity recognition, so on and so forth. However, if we were to go choose the adapter, let's say multiple choice sentence completion, you can see here that we have a few different things. We have the prompt itself that says you are provided with an incomplete passage below, as well as 4 endings in quotes and separated by commas, with only one of them being the correct ending. Treat the endings as being labeled 0, 1, 2, 3 in order. Please respond with the number corresponding to the correct ending for the passage. So here we very specifically choose how we want this LLM to output this result. So here we're making sure that no matter what model we pass this to, it knows exactly what kind of output we're looking for. Then we pass in the passage and the ending choices. So if we hit run, please, you can see that on the left, our adapter chooses the correct option. Option 3, being the last option there, gets them some water to gargle in their mouths. Whereas Mistral-7b Instruct not only chooses the incorrect option, it also misindexes it. When the correct index should be 1, it chooses the index as 2, even though we very clearly stated that these labels are outputted 0, 1, 2, and 3. If you'd like, you can also choose to change what the prompt you'd like it to be. You can manually edit those, but for the sake of time, we're going to kind of move past that for the time being. And that's just, well, yeah, we can also change there. It runs, it'll run the same. And that's more or less what LoRA Land looks like. If you'd like to see any of these adapters more closely, check them out by yourself. All of our adapters are on Hugging Face. Each of those model cards has a code snippet for you to use just to load those weights in yourself and give it a try. And if you're interested in joining us in Predibase, our serverless deployments are available. So you can check out, for instance, Mistral-7b Instruct here. We also have Gemma available, Llama, any of these very big, well-known models are generally available to us as serverless deployments for you to just simply prompt. And I hand things over to Justin to just discuss a little bit of our future work.
Cool. Thanks, Tim. So we've launched LoRA Land. We're doing it at a very low cost point. And so, yeah, what do we plan next? So first and foremost is more adapters. I think the movement, the revolution is kind of starting. There's no data set out there that's safe from experiments. And on this front of more adapters, I think there's 3 things to consider. One is more data sets, right? Why not train an adapter on every LLM data set in existence? And for every one that we do, we should put it on Hugging Face so that the whole world can use it. We believe the future of AI is specialized open source models. So we definitely want to power that movement. But then also, like LoRA itself, we kind of only talked about it briefly, but there's actually some interesting hyperparameters within it in terms of like the rank, for example, where like the original LoRA paper, I think in their hyperparameter search, they didn't find a significant difference in quality between like rank 8 to rank 256. But there's definitely, you can definitely use ranks that are higher than 256 or lower than 8. And it will be interesting to see how that sort of hyperparameter plays with the quality of different tasks. I think as Tim mentioned, there's this whole range of task complexity. And so maybe for the higher ranks, that will improve the fine-tuned models to actually be more competitive with GPT-4. I think another question that's really interesting to ask is, which base model is best? I think, there's many different 7 billion parameters out there. I think now there's, some heat coming up on the 2 billion parameter size. But yeah, which base model is best? And then are bigger models better? So those are just some ideas for some next directions. And then as a more open-ended academic question, I think this lift that adapter-based fine-tuning brings over the generalist models is kind of mysterious in that it does vary drastically depending on the data set, as well as mechanical factors like prompting techniques. And so I know there's researchers out there who are, thinking about this, but, we also want to think about it too. But like, it would be really kind of incredible feat to be able to anticipate adapter compatibility in an upfront way, before you train any models. Can you know upfront if an adapter will be successful? So finally, I think we're going to take, a mixture of our results and our ideas and our experiments and making an academic debut by publishing our work on adapters more formally in the form of a paper in the coming weeks. Yeah, Tim, can you finish up with our final takeaways for today?
Yep, absolutely. So we wanted to leave these last quick things to remember as just something for you to keep in mind, even if you remember nothing else from our presentation. If these 3 things stick with you, we will have done our jobs for today. First things first, is fine-tuning worth it? We argue with especially with Predibase, absolutely yes. By combining PEFT and QLoRA, we provide a fast and smooth fine-tuning experience that optimizes for both efficiency and effectiveness. And you can see just how powerful fine-tuning has been just through our results against GPT-4. Next, how many GPUs do we need for our adapters? With LoRAX, only 1. Predibase is the only platform that is really optimized for LoRAX-based deployments right now. And so this drives down costs down by orders of magnitude for all of our users. And finally, what is the future of AI? At Predibase, we believe specialized open source models are the future of AI. And here at LoRA Land, our results only reinforce our conviction. So if you want to check out fine-tuning and serving in Predibase, please join us. And if you haven't visited LoRA Land yet, come on and give it a whirl. Come see for yourself why we hold our beliefs about the future of AI so strongly.
Cool, thanks. And that's all we have.
Wonderful. Thank you both so much for taking us through all that. And thanks everyone for the feedback in the chat. Seeing a lot of applause, celebrations. Thank you guys. So we have until the top of the hour for Q&A. So I've seen a lot of Q&A back and forth in the chat. But if you haven't had your question answered, or if you have something that's on your mind, drop it in the chat and we'll have Tim or Justin talk through it live. Let's see. Can we use VLLM to run multiple LoRa adapters in one GPU? You guys want to talk about VLLM first? Compare that to LoRAX.
Yeah, I can take a stab at this. I will admit that I'm not particularly familiar with VLLM, but this sounds like the perfect question for the Predibase Discord. We also have a Discord on LoRAX. I think we're actually planning to unify them. So it's just the LoRAX Discord. But let's see. I imagine that it would be very competitive. But yeah, I don't know too much about VLLM to answer that question.
Well, yeah, definitely a good plug for our Discord channels. I'm sure you'll be hearing about those more in the coming days. One question, I think this is a really interesting one. When is fine-tuning worth it compared to other techniques like prompt engineering? This person, Lydia, asks, say I want to have a specialized translation model that translates text based on a glossary and uses specific vocabulary. What does fine-tuning bring to the table compared to efficient prompting?
I can maybe answer this one. Generally speaking, what I've observed through our experiments here is that fine-tuning actually makes the largest difference when it comes to the kind of output that you're trying to provide, specifically when it comes to output structure. So in the case of using, for instance, a glossary and wanting specific vocabulary, I would argue that fine-tuning will probably make a much larger difference than prompt engineering. Prompt engineering is particularly good when you have, for instance, a very small amount of data that you want to provide, for instance, few-shot prompts in which case this can be quite helpful. But in the case where you do have sufficient data to fine-tune on and you want your outputs to be formatted in a specific way, fine-tuning does go an extra distance compared to prompt engineering from my experience.
Yeah, the only thing I have to add to that is what you're describing about, improving a translation model. Like, this is actually like one of the first, as I understand, it's one of the very first motivations for fine-tuning to begin with. It came out of neural machine translation research back in like 2014 to 2016, I would say. I can try to find a paper that I think tries to talk about this very explicitly. Yeah, so my feeling on this is that, yeah, fine-tuning is kind of the perfect fit for something like that. Yeah.
Nice, thank you both. Another question that I can take a first stab at answering, you guys feel free to pile on if you want. Can you clarify the ownership and privacy point and how our approach provides that? So I think this came up on an earlier slide, really in relation to the idea of using open source models as kind of your foundation. The idea of using open source versus a commercial model like an OpenAI model or another is that when using the open source one, you train the model with your IP and your data, and you retain full ownership of those model weights when you fine tune something. You're not reliant on a commercial provider, and you're not kind of ceding ownership of those weights to that commercial provider. So Predibase, our philosophy is we provide the infrastructure management and the tooling for all of your fine-tuning tasks and serving tasks. But when it comes to the actual models and your data, it's your data, they're your models, they're your weights, and Predibase doesn't interfere with that. All right. Kind of a question about latency. What's the latency for switching adapters on one GPU?
Let's see. So I don't know the number off the top of my head. I do think that this might be covered in like the LoRAX, one of the first LoRAX blog posts. But in my experience of just using this stuff for LoRA Land, it's extremely negligible. In fact, you can try to go to LoRA Land and like frantically switch between all of these different adapters and see, what the loading time is. But yeah, once the adapter weights get loaded onto the GPU, they're kind of just there. So like request queues, they'll kind of just churn through. So it should be minimal.
Great. Justin, this could be a good question for you based on some of the recent work that you've led. Any tips on generating input data sets for fine-tuning instead of manual labeling?
Yeah, thanks for directing that question to me, Will. This is, I think, one of the most exciting realms of the AI world right now, which is, what options do you have when you don't have, human manually labeled data? In our case, we have all these open data sets online, so we didn't have to do any of the the labeling ourselves. But one thing to definitely consider here is getting labels from a teacher model. And so this is very much in the realm of synthetic data generation. And teacher models out there, GPT-4 is a good option. The models from Google, Gemini are also a good option. But once you you can rely on them, you can lean on them to kind of get your labels. And then once you have your labels, it's extremely easy to just distill that into, a small Mistral-7 billion parameter model, for example. So that's definitely something I would recommend exploring in terms of like, how do you get started from, from nothing. Yeah.
Great, thanks, Justin. I see a few questions in the chat that are kind of asking around the idea of how fine tuning can either help or kind of be layered on top of RAG pipelines or RAG use cases.
Yeah, so this is not something that I've personally done myself, but there's several papers now out there that are talking about this. One of them, I think, came from Microsoft. I posted it on my LinkedIn not too long ago. But yeah, I believe the conclusion there was that these are separate techniques, but they definitely work together. And so you can imagine, RAG is just the system that is basically a search API where you're, fetching documents and sticking it into the prompt. And then the language model doesn't really need to do anything creative. It kind of just has to look at the documents that it has been provided and then synthesize a, fluid answer. But, fine tuning can still improve the model in terms of how it synthesizes the right answer. Like maybe you want it to just be very, very concise and actionable, or maybe you want it to be like a lot more detailed in terms of like, what it highlights in the documents that have been provided. So in terms of these two techniques, they're separate. I see them as separate, but yeah, you can definitely use them together. And I would definitely do a search for like Microsoft RAG fine-tuning comparison, and you'll probably find the paper where it was a better together story.
Yeah, and just to specifically address, I think there was one question in the chat about which one is better, fine-tuning or RagChop applications. Like Justin said, I think they are fundamentally like separate ideas that should be used in conjunction and not necessarily thought of as opposing each other.
Great, thank you both. There's a question around how much data do you typically need for fine-tuning tasks? I know that's a really big question that probably the answer starts with, it depends. But maybe either talking a little bit about the amount of data that was used for some of the LoRA Land adapters could be an interesting story. And then anything else you want to layer on top of that?
Yeah, I think that this is going to be one that we want to experiment with more in, for instance, our future, in some of our future results. For one, how narrow is the task itself? We find that with very, very narrow tasks where the output might be very different than what a model would normally output, even a small amount of data can actually make a pretty big difference. For instance, some of our glue tasks, I think we're only about 2,000 rows. So even a relatively small amount of data, you can get some pretty big leaps with fine tuning. But again, it is going to come down to the difficulty of the task and the narrowness of the task. And we hope to get a little bit more insight as we continue experimenting.
Yeah. Another kind of practical thing to think about is like fine-tuning LLMs is still very empirical. So you should really just try with a small amount of data, whatever data you have. Try doing it with half of that data, and then see what the gap is. If the gap is big, then that probably suggests that your fine-tuning would benefit from if you collected a lot more data. If the gap is really small, that actually suggests that you probably maxed out. Like the LLMs are probably going to get as good as they are going to be on that data set. Yeah.
Great, thanks. Another kind of technical question about LoRA Land. Is it running off of one A100? And assuming it's just one server, how big? And how does it scale to lots of users?
Yeah, so I believe it is actually just using one A100. I do think our infrastructure, we do have this case of like, oh, if there's like a ton of load that just comes like all at once, then like maybe we'll like grab the second A100. As far as I know, that has not triggered, and we've gotten a lot of traffic, especially on our initial launch day, where I think we were like the top page of Reddit for like, probably a full day. Yeah, one A100 is easily able to handle the load. And this is also completely consistent with, I think, what Tim mentioned about our evaluation harness. So, the way we evaluated these models, we didn't actually run them locally. We just had the LoRAX deployment up, and we just sent curl requests through the REST API to that. And we would basically send these like big batches of like thousands of requests at once. And yeah, within seconds, kind of like it just turns through. Yeah, I think the load that a single A100 can handle is actually quite high. To date, it's still one A100. But yeah, I don't want to recommend to people who are serving, much higher levels of traffic applications to just only use one A100. Like there's probably definitely a world where like beyond a certain level of traffic, you still want to have maybe multiple deployments ready to start. Yeah.
Great. Let's see. Here's an interesting kind of process or approach question. Does it make sense to have incremental fine tuning? So start with 100 samples, fine tune, predict on the next 200, make corrections, and repeat?
I actually believe there was a user who had something similar where they fine-tuned on a certain data set, retrained on their errors, and then continued doing so. If I remember correctly, I don't think the lift on that was as large as we might have expected. Overall, our results seem to have been fairly similar to each other, whether we did iterative fine-tuning or just fine-tuning all on the same data at once. So from my experience, I would say that this iterative approach might not be that strong compared to normal fine-tuning, but it's certainly something that you can experiment with, and it's very easy to do so with Predibase.
Nice. Yeah, I agree with +1 to that, Tim. The thing I would want to highlight is fine tuning here is it's kind of a continuous story. You start with this pre-trained model, but really you can just continue tuning it on and specializing it further and further on different tasks. So for example, in this graph we took this instruction tuned model and we're just fine tuning it. We could also, there's nothing preventing us from just continuing to, further and further levels of specialization. But yeah, definitely something to try. As Tim mentioned, if you fine tune on only the mistakes of the previous model, there's some consequences there. For example, one thing to be aware of is that these models can forget, right? So there are a lot of parameters, but if you have it optimized for too long on sort of one objective, it can start forgetting other stuff that it had learned previously. And so, yeah, I think thinking about balance and thinking about not overfitting, these are important considerations when doing multiple rounds of fine tuning.
Great, thank you. Here's a question. Any thought or experiments you've done on using distillation followed by fine-tuning?
Distillation followed by fine-tuning. That sounds pretty interesting. Let's see. I don't see a reason why it would not work right away. And I would be curious to hear what use case you had in mind specifically for that kind of setup. Yeah, Tim, any thoughts from you?
Yeah, it's an interesting proposition. I don't think we've done necessarily any experiments on that for LoRA Land. I'm trying to think if we did any of those in the past, but certainly one to keep in mind, I think, as we move forward. That might be an interesting one to take note of as we continue with LoRA Land experimentation.
Great. Another question about adapters and fine-tuning. Once an adapter is created, if they want to retrain it, do they need to create a new adapter, or can the old one be further fine-tuned?
Yeah, so I can answer this. So in the Ludwig framework, which is kind of the open source machine learning framework that Predibase is powered by, you can kind of load in model weights and continue training. In the Predibase platform today, you do actually need to set the training runway kind of upfront. And so if you wanted to continue training within the Predibase platform, you would need to just like restart your training. This is a highly requested feature that we are actively working on. And we should have something, I think, in the coming weeks. However, as a workaround, something you can do is any models that you train in Predibase, as Will mentioned, you have full ownership of. So you can really one option is you could just literally download the model. You have the model locally. You can continue fine tuning it locally from those snapshotted weights. And when that's complete, you can re-upload the model back into Predibase. So that's probably kind of a little bit more of an inconvenient workaround, but it should work. And then within the platform itself, it is a feature that we are working on.
Mm-hmm.
Great, thank you. Well, we're just getting ready to come up on time. Thank you everyone for sticking with us through this show. We will be sharing a recording of this most likely later today or first thing tomorrow. So you'll be able to view it on our YouTube. And again, the slides are available in the handouts tab on your screen here if you want to download those. I think we have time for maybe just one or two more questions if there are any. But if not, really appreciate everyone for joining, and we'll be, we're excited to see you on our next webinar, sometime in March. So thank you, Justin and Tim, for all the hard work building LoRA Land and for building this webinar and walking everyone through the approach. I know I learned a lot, so hopefully everyone else did too.
Yeah, thanks so much. See you, everyone.
Yep, thanks everyone.
Take care.